Hey, this is Horner, and this is the first part of the Conservation of Energy and Work in AP Physics C explanations. We remember that there are two basic types of energy. There's plenty of other types of energy, but these are the two basic types that we typically work with. Kinetic energy, or the energy of motion. We see the equation for it. We remember that it is measured in joules. And then we also have gravitational potential energy, or energy of position. And that one, your equation is here, and that one is also measured in joules. So we want to know, where exactly did this come from? And I think that's really the big thing that AP Physics C does, is you'll go beyond just seeing the equations, but you actually kind of know where they come from. So we're going to start with free fall, and we're going to end with conservation of energy. So we're going to start with the definition of acceleration in the y direction. And we know that because we're going to just say that down is negative, or if I start here and I fall, I'm going to lose potential energy. We're going to call this negative g. So let's go ahead and use our equation. We know that the final velocity in the y direction squared is equal to the original velocity in the y direction squared, plus 2 times the acceleration in the y times the change in that displacement in the y direction. So this is equal to the original velocity in the y squared minus 2g, and then we have yf minus yo, where f and o are final and original. So our equation that we're going to use in the end is just going to be vfy squared plus 2g y final. So here's our final conditions, and that should be equal to our original conditions. So this is v original y squared plus 2 times gravity times our original position in the y. So this is just the conservation law for free fall. So the conservation law for free fall. Let's go on and take a look at something that's in free fall and think about the net forces acting on it. So the sum of the forces of something falling in the y direction, we know that that would be equal to the mass times acceleration in the y direction. Let's go ahead and say that the sum of the forces are going to be equal to mass times the change in the velocity in the y direction all over the change in time, or dv over dt, and that is equal to negative mass times gravity. So here is our sum of the forces, so that's just m times that change in velocity over change in time, and that's equal to negative mg. So remember, we defined ay as negative g. So let's actually use this to do some things, and we're going to use calculus. So at this point, we're going to look at the chain rule. So we're going to use the chain rule, and we're going to use the chain rule in a little bit different fashion. So we really want to know if I have dvy over dt, if I think about the chain rule, and instead of using dvy, instead of dvy over dt, let's do dvy over our position, which is dy. So instead of differentiating versus time, let's do it versus dy. And so now we can say dy over dt. So we've used the chain rule to kind of flesh that out. And now what we'll do is say, well, dy over dt is the velocity in the y. So that's equal to velocity in the y times the change in velocity in the y over the change in the position in the y. So here we don't have any position in the y, and we really badly need it. So we use the chain rule, which means that we're going to put dy on the bottom, basically dy on the top, and you could think of just moving the dt over to the right underneath that dy. So nonetheless, this guy right here becomes vy. So now we've got vy times the quantity vy over dy. So now that we've done that, let's go ahead and plug in our Vy times dVy over dy into our original equation. So here we know that we use the chain rule to do the derivation of this. So when we use the chain rule, we ended up with this. So this guy right here and this guy right here are the same. So now we're going to say m times Vy times dVy over dy is equal to negative mg. So we've set up a differential equation is essentially what we've done. Not meant to scare you at all. It's not a hard thing to do, but it's really important for this derivation as we go through. So now at this point, what we want to do is we remember that we had an original velocity in the y and a final velocity in the y. So let's on this side integrate. So we're going to start with our original velocity in the y, and we're going to take that to our final velocity in the y. Over on the other side, we're going to do the same thing, and we're going to look at negative mg, but we're going to add to that dy. And so we're going to integrate this side. So we've used the chain rule on this side also. And we're going to say y original, and we're going to go to y final. So we're just looking at this left side and what happens when we go from, when we do the integration of this and we go from the original velocity to the final velocity, and what happens to this side when we go from the original height to the final height. So let's go ahead and let's go through and do that. So if I'm going to do the integration of this, we know that m times Vy, and we're differentiating in terms of dVy, so we're going to end up with 1/2 because we know that this is going to be squared, so that's 1/2 of mVy squared, and our constraints here are VOY, and on the top we're going to have VFY because we're going to go from VOY to VFY. And then on the other side we've got negative mg, and then we're differentiating here using the dy, so that now becomes y, and we're going to go from y original to y final. So let's go ahead and finish up our integration. So we'll say 1/2 of mv, and then here we're going to do the final. So mv final y squared minus 1/2 mv original y squared is equal to negative mg, and then we're going to do y final, and then we're going to subtract from that negative mgy original. Negative and a negative make a positive, so what we end up with is 1/2 mv final squared plus, so now I'm going to take this and move it to the left side, and that is mg y final, and that's equal to, so a negative and a negative are positive, and if I take this and move it to the other side, I end up with 1/2 of the mass times the original velocity in the y squared plus mg, oops, that should be a plus, mgy original. And that should look very familiar. Remember, this is kinetic energy. This is potential energy due to gravity. This is our final kinetic plus our potential energy due to gravity final, and that's equal to our original kinetic energy plus our final potential energy, original potential energy due to gravity. And so that is our conservation of energy coming from the free fall. And you'll notice that this equation kind of goes along with this one, just trying to compare how you can kind of see what's happening in terms of just adding the mass. Now remember, your mass won't matter when this goes through. And if I multiply everything by 2, you end up with this equation. So we have now found this equation. Going through and starting with sum of the forces is equal to the mass times acceleration in y, and then using the chain rule. Once we use the chain rule, we can then differentiate. We can then integrate on both sides. Once we integrate both sides, we find out this equation. We cross off our m's. We multiply the whole thing by 2, and we end up with this conservation law for free fall. So kind of a neat little derivation from calculus.